All right, guys, let's get started. So if you, I've already added the slides for the first. You already had the lecture one in your course. So I added the slide for the lecture number 2 and 3 because the last session students were asking me. I mean, I tried to be like super slow to just leave you some time to take note and if you want to take a picture. But since many students ask, so after each session, I'll try to upload the slide of the day, so you can find it under the folder slides, maybe underscore section 101, which is related to our section. I'll do it every session after I double check if I had any mistakes or not. Since quite often I do that, and then you can find it later the day there. Also, I'm trying to record the screen so you guys, whoever missed the class or whatnot, maybe every week or so when I had a time, I probably upload them maybe in YouTube because the course didn't have enough of space for that. I've already added the first lecture. So if you Google my name on YouTube and then there's a playlist of the course, you can find the first lecture. And so every now and then I'll try to upload these sessions there, so you can have, you can match with the slides as well. For those students who are not here, you can just, let them know as well. All right, so lecture 4, we're going to start talking about loss functions and also can we generalize learning functions. So a review of the last 2 lectures, a quick recap. So we started by mentioning that if we had these 3 different properties. So first of all, we didn't have any mathematical formulas or analytical formulas for a problem. And also if we found that a pattern was, a pattern existed and could be discovered on the problem we wanted to tackle, and also, the most importantly, if you have some data on it, we can apply learning methods. And we talked about a little bit about supervised learning, in which we're going to have an unknown function, and we have a data set. Through that data set, we want to derive to a learning algorithm that picks our candidate hypothesis, which we call it G. And that candidate hypothesis will mimic the real function f that was unknown to us. So I left the link of a very nice tool you can play with. I'm going to show it to you in a second. So if you remember the last lecture, I was talking about PLA and how it does converge to finding an optimal separation between your binary classes. In that case was pluses and minuses. So I'll leave the link here, so just have a quick look. So you can, add or remove your data points. So like add greens or add reds, but make sure it's linearly separable. And then you can just reset and either do it by an animation, like automatically. It's gonna search for all the space, which was misclassified, and then it found the correct line. Or you can just, play with the and reset it, then I start training step by step. It's going to search for misclassified, and if it found one, so this one is like hidden here. So that was the correction of the weight I was talking about, and it's going to push the classifier left and right with different slope, and finally it's going to find it. There are other bunch of hyperparameters here that you're going to learn later, mostly for your neural network lecture that I'll talk about later. So that's not a bad tool to play with in order to gain more insight about PLAs. All right. So now let's talk about the feasibility of learning in other sort of environments. So suppose you have a bin of marbles, and inside that marble you have 2 different classes. So you have green marbles inside and you have red marbles. And you know that with an unknown number that we call it mu here, there's a probability that we have certain number of reds inside that bin of marbles. Like, I don't know, 40%, 50%. And since there are only two classes, so whatever number for mu we had, you just have to, deduct it from the one, and then it's going to be the class, it's going to be the probability of the other type of marbles, which is going to be green. So, and through that bin of marble, we take some samples, in this case 10 samples. So by taking 10 samples and taking a look at the samples distribution like this, you can see on this side, here, you're going to see that sometimes you're going to have the same number of distribution or same number of red marbles just as what you had inside the bin. So in general, we wonder, and we call this fraction of red marbles here with the Greek letter nu, that sort of V shape. And we wonder, are these two are related or not? So if we take certain number of samples from another distribution, these two probabilities can be related, if yes or no, and how. So as I mentioned, so we're going to have a probability of picking red marbles, and we call it mu, and the other one, picking greens, would be 1 minus mu. And in general, the value of mu is unknown to us. And we notate nu as the fraction of red marbles in the samples we took out of that marbles. Now we're going to see, can we relate these two together? How can we estimate these two? And if they are far from each other, by what threshold they do? All right. So we're going to have the first question. Does nu say anything about mu here, do you think? Any suggestions? Okay, early Monday morning. What is it? All right. So in general, if you take several samples from your bin of marbles, one of the samples, one of all those 10s could be all green, right? It happens, might be. Or the other way around, might be that all the samples might be red, or you have like 90% red, 90% green. So in general, they don't say anything in relation to each other, because samples can be mostly red while the bin was mostly green. However, the sample frequency, so if you take enough of sample and then you take the average, these two tend to be close after a certain number of samples, right? Because these samples, after all, were generated from another distribution which was inside the bin. So you can expect they're likely to close, to each other, but at some level, but you don't know how. So the question 2 is, what does exactly nu say about mu here? And then, as I explained, in a big sample space, when we have our, a large number of n, probably nu is going to be close to mu within a margin, and we don't know that the margin is for now, and we call that margin epsilon. All right, does that make sense? Okay, now we're going to see how we're going to define a sort of a bound or an inequality so that we can express the relationship between mu and nu here. So in the mid 60s, a guy with the name Hefthings so came up with the idea of Hefthings inequality, and I put the reference paper there, 1963. And he was basically saying that when you take enough of sample and when you have a large number n, chances are that your nu number is going to be close to mu within a threshold, epsilon. And that was later known as Hefting's inequality. And basically it says this. So this is the, let's see. So this is the difference between your mu and nu, and he was basically saying that if you take this n number large enough, the chances that these two are close to each other within epsilon. And the higher the epsilon is, the worse the case would be for you, because it's going to be a bad news for you. You want to make sure that these two are closer to each other. And since this inequality is coming from an exponential raised to, so Napier's number, so this is going to be your function y of x, that at point 0 it hits 1, and then the more it goes toward the positive number, it's going to raise exponentially, and the more it goes down to the negative number, it's going to go closer to 0. And so you see, and this will say that the probability of this would be closer than something, smaller or equal than something. And you want to make sure that this is as small as possible, because if it goes way beyond 1, it doesn't help you in your problem, because you knew that the probability of everything is smaller than 1, right? So the good news was at some point that if you take the number n as large as possible, and since you have a minus here, so it's going to bring down your function to the minuses here, and then you're going to hit closer to 0, right? And it's going to be not bad. But the point is, this one is multiplying with that epsilon that you wanted to choose as small as possible, and this small number is has been raised to 2, so you're going to have even more smaller number, and then you multiply these two, and it's going to take out all the positive effect that you will need from that big number from that, and then you're going to have again a large final number on this side of the equation. So that's an interesting inequality, and we're going to come back to it in VC dimensions and the complexity of the problem later on. Just wanted to drop it here just to have a good sense of what's going to happen later on in some other chapters. And it's going to gain you some insight how to define complexity of defining functions in learning models. All right. Let me just clear all these things. Yeah. So in another word, the statement says that mu is equal to nu here, but it's not quite equal. It's a pack equal. So this one represents probably approximately correct. Probably because you had this here. Probably because you had this here. Approximately because you want to approximate it within epsilon, and that's why you call it PEng. Later on, we come back to it when we start PEng learning as well. So, yeah, just wanted to mention it right now, that you have some ideas about the other things that you're going to learn. Any questions so far?
So do we have any conditions for taking the samples? I mean, it's like how large of the population?
I'll go back to it. Yeah, yeah. All right. So now that we know we have this inequality in connection to just taking some samples from a bin of marble, can we connect this to our learning problem that we already had and our supervised learning? So in this case, our bin in our bin environment, which we just saw, the unknown is a number mu, as I mentioned. However, in the learning problem that we had in the past couple of lectures, the unknown is a full-fledged function of f, which maps x to y, and x was a d-dimensional space, if you recall, from our credit card application or our recommender system application. So how can we relate these two? How can we connect it? So, if you want to connect these two words, we can assume that that bin of marble represents several points of in our space of data, like this, a big X, and each of those marbles inside that represents one of our data points from the big space, like one of the X's inside our big X. In that case, this turns to this, and using the hypothesis that we knew before, so we can say, we can describe the two conditions, green and red. So the hypothesis got it right. If the hypothesis got it right, which was h of x was equal to f of x, we're going to have the green marbles. And hypothesis got it wrong, we can define that it was classifying for the red marbles here. Is it clear? We just related this to that learning that we already knew from the previous lectures. So instead of talking about those being separately, we talked about them as a point of data, and we use hypothesis set to get it right or wrong in both cases. So in this case, we can define these two classes in our data. All right, now let's go back to the good old learning paradigm that I described in the second lecture. So we had this. So we were starting from an unknown function. We used the training examples and our hypothesis with the learning algorithm, and then we came up with the final hypothesis. So if we plug in that notion that we described in the previous slide, it's as if in our training set, the x's that used to come from, I don't know, user's rating or in a credit card application, it was for the history. So now we can plug in as a probability distribution P on X. So those X's are coming from, for instance, this distribution. And we can plug it here and, you know, follow up with the solution just as before. All right? All right, now let's just talk about the two notations for learning that we're going to use more often from now on. So we're going to define two things here, En of x and E out of x. So remember, these were like 10 samples we took out of our bin of marbles, and we were discussing about the probability of having red inside the sample, and also finding a way to relate this probability with the one inside the bin, which is outside this sample. So the name comes very intuitively, so that's why you have it En, because this is the E for in sample, the sample we had, and that's E out is for out of sample. So these are that out of the sample we have. Okay, now we're going to discuss what are these two. So we can define that both are mu and nu depends on which hypothesis, you know, which is H in this case. Both of them are coming from the same H. Thus, nu or V is in sample, and we call it E of N of H. And mu is out of sample, and we call it E out of H. So if you want to plug these two to our everything's inequality, so just instead of having that mu and nu, we can just, you know, plug in these two, right? So mu and nu turn to the probability of these two, En of H minus E out of H, are within a certain epsilon, and these two are representing a probability less than or equal to some number, some values. But here, by defining this, we got a small issue, because we didn't actually learn anything about the sample distribution of this bin. We just verified it. We just mentioned that, okay, if we have this sample, the difference between these two, we verify that we have a difference by an epsilon number, but we didn't learn anything. We just verified that, okay, this is happening within certain epsilon. So here it goes. A small definition and differences between learning and verification. So here, first, our agreement between hypothesis and our edge was only one edge, right? Because we had only one bin. And for this specific bin, that we had this edge for, the nu generalizes to mu in this case. Thus, using our edge, our hypothesis, we can only verify if the edge that we picked up here in this case, the edge that we picked up in this case, is good or bad, right? But this doesn't tell us anything about the learning. We cannot, do predictions with that. We can just say, okay, we verify, and after taking samples, that specific edge, is it good or bad, or how bad is it? But we would like to learn from this and come up with the edges that describe the problem. And on that case, there's no guarantee that your mu would be small, because you might have one of the samples as all red or one of the samples as all green, like the worst case scenarios, right? Additionally, if we have multiple bins, what's going to happen? Or different people takes different edges, to different hypotheses. How are we going to describe that? How are we going to plug it into the inequality? And that's called learning that we need to know. So I want everyone to understand this. Is it correct? Is it intuitive for you as well? That we have verified actually. We didn't learn anything, right? I'll stop for like 10 seconds to just the thing song. All right, thus, after seeing this that we could only verify, not do any learning, we need to generalize this process to multi-bins. Yeah.
This multi-bins, you're talking about the big thing or the sample?
Yeah, I'm talking about this. So when you have multi-bins, like a different number of bins with different distribution, and you take different samples from each of the bins, thus you have for the bin number one hypothesis, and the out of sample, or the one that is out of your sample, we call it mu. It's going to be mu1, and the one you sampled from the first bin, we call it nu1. So you see that there are different. You could have different number of the distribution between your red and greens. While on the second bin, you could have another hypothesis. We call it H2, and you have another thing, another distribution inside mu2, and thus you're going to have another nu2, right? And you have m of these. So that's why we call it multi-bin. So if you want to generalize this, we're going to have a problem, because Hefting's inequality doesn't apply to multi-bins so far. We didn't discuss anything about it. So how can we do that? And that's going to be discussed in the upcoming slides. So I'm just going to stop here for 10 seconds. Yeah. Oh.
Sorry, why does the inequality not apply to multi-bins?
As of now, it will, because that inequality doesn't take into account different number of bins you have with different number of hypotheses. It assumes that you only have one edge, right? if I come back here, see it applies only to a single beam with one edge, right? You want to incorporate your different edges that comes from different beams. That's why we have to change the inequality in a way that it supports that as well. Yeah.
So with the multi-beams, is the problem that you want to find the probability of getting like a red marble from all the bins, or independently from each?
Yeah. Suppose you have like m beams, and you took like some samples of 10 from each of those m. How does this relate to each other? It's gonna be different, right? Just like this photo.
So it's not like independent bins.
They're independent beams, right? They're independent.
So what if you just do what we just did for one independently on each one?
Right? But since we have different edges, how are you going to incorporate those edges inside? Because each edge describes one of the hypotheses for each of the beams, right?
Yeah.
Suppose I'll have two examples after this, yeah, and you're gonna completely take the information, no worries. All right, now we're going to incorporate the information of multi-beams into that inequality that we described. So it's as if the generalization, let me just read what I wrote. So the generalization will be the union of the probabilities for all the m beams, right? This is the union. So if you recall what G was the candidate that you chose among your hypotheses. So the one you chose that worked the best, you called it G. And that had the highest efficiency or highest accuracy depending on your problem, right? So you can define the previous notion for the Hefting's inequality for that G. And that G, because that was the best of your H's, is always, because it was the final hypothesis, it's always bigger than the probability of your H's, each of the H's, right? Because that was the G. So for the first beam, now we have the same Hefting's inequality, P of E of in of H1 minus E out H1 within an epsilon. Or for your second beam, with a different distribution of green and red, you're going to have this for the second edge. Or you can carry on this way up to your last beam, which was the mth one. So E in H of m minus E out H of m. Like m times. So now, if we take a union of these m's and incorporate them to the inequality, we're gonna have the summation of all those, starting from m1 up to big M. And instead you can call each of these h's hm now, right? So G, if you recall your that diagram that I mentioned in the last lecture, so G is the candidate hypothesis that you choose among your hypotheses. So you have like within your big H, which is a set of all your hypotheses, H1, H2, up to Hn. So when you pick one that works best on your problem, and you pair it with a learning algorithm, so that's going to be your candidate hypothesis. And that H becomes G. It's one of the H's that works the best on that problem, right? Yeah.
Previously, when you talked about G and how it's the best out of the edges, those edges were for the same problem.
Right.
But these edges are not the same problem.
Yeah, and that's why we want to generalize it. We wanted to see that can we generalize from a single beam to multi-beam within certain threshold. That was the whole generalization. Can we generalize? So by having the same method, can be generalized to different distributions of data set with different edges. And that's actually what we're discussing now. Good question.
Can you explain that again, the sum? What are you doing with the sum?
The sum, it's just a union of all these, right?
Okay, but then that probably
Because that probability could be this for the H1 or this one for the H2, or we can pick for the H3 or a summation of that. That are all, within this an epsilon, right? Sure.
How does this help us find a better hypothesis?
I'll explain in a minute. All right. So now that same old inequality on the right side turns into you have to sum up all those 2 multiply Napier's number raised to -2, epsilon raised to an n, and then it's as if you multiply it m times. And that's going to be your final generalization of, things. So here, so this value, which is your h's, is greater or equal to this, all your h's, so that was your g's, and this is less than equal to 2 to multiply m bins of u that you have with the same inequalities. So now we're going to have 2 questions, and that will answer both of your questions now. You're going to see what are the differences between having single or multi-bins. So I'll stop for a second. You can write it.
In that formula, are we counting for all marbles in all the bins so that the probability can sum to 1, or?
We consider all the distributions in all the bins, right? Yeah. Because we want to have a generalization of all those different distributions.
Sorry, don't the last 2 lines contradict each other? You multiply by m is the last one.
Last 2 lines contradicts.
Isn't one of them is an extra multiple of m, right?
Right.
How do they? Oh, yeah, no, I'm sorry, I don't see how.
Oh. I thought I had another mistake. Yeah. Is it clear?
No.
Why not?
Why is the second last line that? Like how can you just add the probabilities together? Can you get a sum greater than 1 as a result when you have to divide by?
Yeah, sometimes this inequality might come up with a higher than 1. Like it might just happen that depending on the n and your epsilon, you have here on this right side it's going to be like 10. But you don't care because even greater than 1 is like the worst situation. So it's going to be like the definite. This is just an upper bound. It could be even more than 1. Right? No problem. Yeah, but keep asking questions because you sometimes find my typos or mistakes somewhere. All right. So now, yeah, let me just. Right, yeah. And that's why it still is. So, I mean, I didn't have enough of space to fit this one as well. So this actually is here, right? So this one is greater than this, greater than equal to this, and this one is greater than equal to that. this comes here. All right, let's have two simple questions with coin analogy. So first, suppose you have a fair coin. A fair coin is one of the coins you normally have that has, half probability of coming head and half the tail. Suppose if you toss that fair coin 10 times. So what is the probability that you get 10 heads? Can anyone say it?
5 to the power of 10.
What to the power of 10?
Well, whatever the probability is getting heads to the power of 10.
Right.
Pair of coins is 0.5.
Right. Yeah. So it's so every time you have 50% chance of having tail or heads. So you do it 10 times. So you have to multiply it to 10 iteration that you had. So it's as if you raise that probability to 10, right? And it's sort of equal to 1/10%. Okay, and this explains sort of having one bean, right? Now let's discuss another more tricky situation. Suppose you have, suppose there are 1,000 people having each having one fair coin. So you have 1,000 fair coins, and each of them toss 10 times. Okay. So now what's going to be the probability of having at least one or some heads? So if you have 1,000 fair coins and you toss them 10 times, what is the probability you get at least 10 heads? Can anyone describe how we're going to approach the... I don't want the final number, but just, the way you approach it.
Could we sum them up?
We sum them up, like each of the thousands?
Right.
But those thousand, like how can you sum it up?
It's like...
Are they dependent or independent? Because you sum it. Because like all 1,000 are dropping like 10 times. Like you have, suppose you're 100 people, like you had 1,000 people. Yeah, I think.
I mean, like for the first portion, it's like a P point, and some P1 to P songs. We can assume the independent.
Okay.
So for this question, if you assume that all the coins are the same.
All the coins are fair, not the same. Like they have,
But fair
like,
means
they have
that-
50% chance of head or tail, right?
Yeah, so if the distribution is the same, then is it the same as one person tossing 10,000 times?
You're gonna see why not. And that's exactly describe why when we had only single bean, we couldn't describe inequality to the multi-beans here.
Yeah, but the multi-bean had different distributions.
These distributions are, you have 50% chance of taking green or 50% chance of taking, red. But the samples you take out of them are going to be different, right? You might, in one of the samples, you could have all greens. In one of the other samples, you could have all red, right? We want to see that it sort of describes the worst case scenario that something, when something goes wrong, it will, right?
So when you're saying some of the coins, that's just
Some or at least one.
1 and 0. Okay.
Right.
Could we sum up from 1 to n of n choose k times 0.5, like n choose k over n is the number of coins, and then this probability?
You're getting closer. Getting closer. So you can even approach the problem with the complement of this problem. The complement of this problem is, so when we want to have the probability of having some coins to get 10 heads, it's as if you deduct this number from 1, which was a complement problem, that at least 10 heads you're going to have for all the coins, like the complement problem of this. Can you calculate that problem? So instead of having some of the coins to get 10 heads, how about having all the coins, all those 10 times, or tails? So the complement side. Start with that maybe. All right, let's have a look at the answer. So we wanted to calculate the probability that some of the coins in our 10 times tossing of 1,000 fair coins to be turned out heads. So, which means that probability, it was as if we deduct this number from -1, which is, so this is the complement problem, that each of 1,000 coins comes up tail at least 1. So that's the complement problem to this. And you would put 1 here, and this problem could be described with, again, that thing that we had on the first question. So 10 times you toss the coin, so each of them was 50% chance. So, and you had it 10 times, but this was done 1,000 times by 1,000 coins, and you would deduct this number to 1 because you wanted to have the probability of the coins to come at least once. And then you calculate this, and it's going to turn out 37%, and you deduct it to 1, and then you see the chances that this goes wrong is very high, actually, like 63%. While the previous, you had only 0.1%, right? You see how big of a difference is it? It describes when you have many m's here, chances that something irregular happen within that distribution is very high, actually. Yeah? All right. Now let's talk about the loss function. You might have seen in the, I'm not sure if you saw the notes that Professor Christie was sharing on Quercus. So that notion, if you saw, so that was the whole story of coming towards that notion E of n, which was describing the loss function in our prediction. So how are we going to define the loss function? So it's actually the average number of misclassified points from your x1 up to xn's, and en, which is we describe here as in-sample error. So en of h, your hypothesis, is equal to the average number, so 1 over n, of all the misclassified point. So the summation from I to n, those hypotheses that you choose for xn minus the real or the true xn, and then you raise it over 2 to find the differences. So how far you were from your prediction to the true value. So the other way you might see it elsewhere as a notion of vector. It's that the number of times your h of xn wasn't equal to xn, so you had misclassified point. You can also define it in another way, which is still the same. So in sample error of h is going to be again 1 over n, and a summation I from 1 to n, those times that your estimator wasn't equal to your true value, which is exactly the same, and this is called indicator function. So this sort of one shape or I shape like. So that was your estimated value. This is your true value. And then you can find the indicator function of A as either 1 or 0. 1 if x was from 1 or if x was true, and 0 if x wasn't 1 or if x was false. So that was very intuitive in order to calculate the loss function. So the average number of times you misclassify your point. All right. So I guess I have to stop for now. I was telling your colleagues, to those guys who came late, I'll try to put the slides of each session at Quercus. You can find it under the folder slides _ section 1. And every now and then I'll try to upload the videos that I captured from my screen on my YouTube channel. So if you search my name and you find the playlist, you can find the videos every now and then. All right. Have a good day, guys.